Okay, so in this presentation, I'm going to provide an overview of how we can implement homomorphic encryption with the ElGamal encryption method. Okay, so there's three main methods that we use to implement a public key: RSA, elliptic curve, and ElGamal. So what I'm going to try to do is to show you some of these methods. Okay, so with public key encryption, what we have is we have Bob and we have Alice. So with public encryption, we typically use this to sign for things. So Bob has a public key and a private key. He then encrypts something with his private key. So that could be the hash of a message, and then sends that over to Alice. Alice then takes Bob's public key and then decrypts what Bob sent over, and if it all makes sense, then Bob has proven that he has a private key that relates to the public key. So this is what's known as digital signing. But we can also use it for encryption too. So we could take something like a key that Bob and Alice used, and we can pass it by Alice sending Bob an encrypted version of the key that we want to use, encrypted with Bob's public key. Bob will then use his private key to determine what the key actually is. So public key encryption is used for encryption, it's used for signing, and it's also used for key exchange. So the core methods that we have include RSA. So with RSA, we take two prime numbers, P and Q. And then the difficulty of this is to be able to factorize P and Q, factorize N back to P and Q. The other method that we have is the elliptic curve method. So we use an elliptic curve, we take a point on the elliptic curve, and then we add it n times to get another point. The public key becomes the point that we've calculated, and our private key becomes the number of times that we've added that point to get the resulting public key. Elliptic curve is typically used these days because it's relatively fast compared to the large key sizes that we have with RSA. The third method that we have is what are called discrete logarithms, and one method that we can use is called the ElGamal method. So let's see how this actually works in practice. So if we have Bob, and Bob needs to create a public key and a private key, and then we have Alice. Initially, Bob creates a generator value and a prime number. So this is typically a large prime number, 512 bits or 1024 bits, and the generator value is a value between 0 and p minus 1 that's selected. So initially, Bob creates a private key known as X. Probably this is a 128-bit random value. Then Bob calculates G, this value, to the power of X, and then in finite fields we use mod P. The advantage with using mod P, so that's the remainder after a division by P, is that all of the maths, such as multiplication, addition, subtraction, and so on, will still work even though we're using a finite field between 0 and P minus 1. So Bob's public key becomes Y, G, and P, and his private key becomes X. So he will send his public key to Alice, but he'll keep this key, this value here, as secret. So the way it works is that we calculate whenever Alice is sending Bob an encrypted message, she calculates two cipher messages. For A, she takes G, and now she takes a random value K. So this will be random for every message that is sent. Then she takes the mod of P. She calculates B, which is equal to Y to the power of K times the message that she wants to send, mod P. So these are the two things that she sends as her cipher. So when Bob received this, he calculates the message as B divided by A to the power of X. So X is his private key, and obviously mod P. And we can trace this through because B is equal to Y to the K M, and A is G to the power of K to the power of X, as we saw before. Now Y is equal to G to the power of X to the power of K times the message. And this here is G, because of logarithms, is equal to G to the K X. And then that is equal to G, because of the way the logarithms work, to M divided by G to the X K. These two cancel out, and we end up with the message. Okay, so if we see what we've done, we've created a private key. We then create a public key, which is G to the power of X. The difficulty in discrete logarithms is it's difficult to find the value of X that created Y given G and P. We send the public key to Alice, but keep this private key secret. Alice gets her message, and then creates an A value, which is G to the power of K, which is the random number she's just created. And we see the K never appears over our calculation. Then B is Y to the power of K times the message, mod P. And then Bob did this calculation here. This is what's called the inverse mod function, mod P. It's our divide. And then in the end, we end up with the message back again. So that's the basics of ElGamal. Okay, so this is what we've just looked at. Y is equal to G to the power of X, mod P. There's our A and B value, and there's our message there. So as we did there, that all calculates, and we end up with the message. So this is the code that gets us there. So I'm using Go here. G to the power of X mod P equals Y. And here are some values for G and P that are safe. These are the values that are taken from Diffie-Hellman, 512-bit prime number, 768-bit prime, and 1024-bit prime, and these are the G values that relate to them. So we can actually select different values for the prime and also for the G value. So here are the values here being calculated. So A is equal to G to the power of K mod P. K is just a random number up to our prime number, -1. And then we take the message, multiply it by y to the power of K, and we end up with that. So that gives us our A and B value. And then when we decrypt, we take B and we multiply it by the inverse of A to the power of X. And we say mod inverse of that value. So there's A to the power of X, mod P. And then we take the modulo inverse of this with respect to P. And that gives us the 1 over A to the power of X. And that gives us our results. Okay, so here's a simple example of that happening with 512-bit encryption keys. We can put in a message here, and we'll put in a private key here, and it should all work out perfectly here. So there's a public key, there's the A and the B value, and so on. So the code in Go is this here, and we can see how that works out. We can ramp up and use bigger prime numbers, and you see each time it increases the values that we have for our ciphers and should make it more secure. So let's look at the homomorphic encryption part of this and how this actually works. Okay, so for multiplication, so we'll just go back to our device here. Okay, so if we remember, what we had before was that y was equal to G to the power of X mod P, A was equal to G to the power of K mod P, and B was y to the K mod P. So what we want to do is to multiply two values together with our cipher values. So that means if we take the encrypted value of value 1 and multiply it by the encrypted value of value 2, we end up, when we decrypt it, we will end up with value 1 and value 2. We should end up with value 1 times value 2. Okay, so we cipher one value, cipher another value, we multiply them together, and then we decrypt with a private key, and we should end up with the multiplication, which means that we can keep things secret here and still operate on them in a mathematical way. So the basic mathematical operations that we have are multiply, divide, add, and subtract. Some methods are partially homomorphic, such as RSA, which can do multiply and divide. With ElGamal, we can actually modify it so that we can also get addition and subtraction, and I'll show you that later on. Okay, so there's the basic methods. So if we now take our A value, so we'll say that A1 is equal to G to the K1, and I'll leave off the mod P just now, but if you just assume that that's all used, and then we'll take Y to the power of K1. So K1 is the random value that we create for our first cipher, and then we have the value M1. Then we take a second number, and we have a random value for this, and we'll take that, and we'll take the second value. So is it possible for us to take these two cipher values and then create M1 times M2? Well, it works because we just take this as we had before, and now we multiply the two ciphers together, multiply them, and then we do our divide again, and it should all work out. So we can go through the maths if you want, but it should all really just cancel out. So that's g to the power of k1, and then b2, b1 is y to the power of k1, y to the power of k1, m1, and b2 is y to the power of k2, m2. That's divided by g, which is g to the k1 to the power of x, and g k2 to the power of x. So we should find when we multiply it all out, then these all cancel out, and we're ended up with m1 times m2. Okay, so this is what we have here. So just as we had before, we will multiply, and we should be able to get the answer from there. For division, it's slightly different, but this time what we do is that we will flip the value around. Okay, if you remember that we had this the last time, if we now want to divide, we take b1 and b2 here, and a1x, and flip it here to x. So this is equivalent to a divide operation that we saw before. So what we should end up when we decrypt it is m1 divided by m2. The value that's m1 divided by the value that's m2. If we flip, so this is the values that relate to m1 when they're ciphered, this is the values that relate to m2 when they're ciphered. Basically we just flip it around for the multiplication, and then that's equivalent to the divide operation. So here we are here, so it's equivalent, but we flip the values over, and we do that using the mod inverse of A and the mod inverse of B will do that flipping for us. So here we are here for a division, so let's say it's 24 divided by 3, and we'll just try that out, and we see the result is 8. 36 divided by 12 is 3. Okay, so the code that we're using is here, and in this case we flip the A2 value and the B2 value round, and then we can still do the multiplication as we did before, and it should all work out. We can try it with different prime number sizes and it should always work. As I said, the larger that we have our prime number, the more secure that it will be. But where it gets really interesting is when we have addition and subtraction in discrete logarithms using homomorphic encryption. So with this, what we can do is we can add up values that are encrypted and get a result. So that might relate to the number of Bitcoin transactions that Bob has had. So we could tally them up with encrypted values and still know what the result, how many Bitcoins he has in his wallet, and whether he can pay Alice. Okay, so let's have a look at this one. Okay, so we do this one slightly differently. So if you remember, what we had before was that y was equal to g to the x mod p, and a was equal to g to the power of x mod p, g to the power of k mod p, and b was equal to y to the power of k mod p. With additive homomorphic encryption, sorry, there should be a message in there. With additive homomorphic encryption with ElGamal, what we do is we modify the b value so that the b value becomes y to the k g to the power of m mod p. Okay, so we see how we've modified it there. Now it becomes g to the power of the value that we want to be able to add. So this modifies the b value so that we can now get additive functionality to it. So if we now do our calculation, which is b1, b2, and a1 to the power of x and a2 to the power of x, then we get g to the power of m1, g to the power of m1, and then that's y to the power of k1 here, and g m2, y to the k2. That becomes g k1 to the power of x and g k2 to the power of x. And then when we replace y, we get g m1, g to the power of x k1, d to the m2 to the power of x k2. Okay, so k1 is the random value for our first value, m1, and k2 is a random value for the second value, m2. So then we end up, because of logarithms, with this. We can then gather together here, and that's g to the xk1, g to the xk2 over g xk1, g xk2. These cancel, and we end up with g to the power, because of logs, g to the power of m1 plus m2. So m1 is the value that we've ciphered, and m2 is the other value that we ciphered. So now what we do, we don't have a value of k in there at all, there's no random numbers. Now what we do is that we search the space for gi. So we keep searching from 1 to possibly 1,000,000 until we find a value of I that matches g to the power of m1 plus m2 mod p. So we keep searching and searching for a value which will match this result here. Once we've found it, then we have found the total of m1 plus m2. It's kind of magic, but it works very well. So in this way, we could have multiple values that we cipher. We then multiply them all together, multiply each one at a time, and then we'll end up with g to the power of m1 plus m2 plus m3 and so on. And then to find the total, we just have to search through the values of g to the power of I when I moves up in value, mod p, until we found the value that equals that one. So I hope that makes sense what we're actually doing there. I'll show you in code in a little minute, but this is the key factor here. We can find the summation by searching for it. So it's a brute force, but we don't have a lot of values that we need to search for. Okay, so here it's here. So here's the basic working add. We change this the value here, so it's g to the power of m1 rather than just m before. That's what it was before. So if we look at the code for this one, show how that becomes. Okay, so there's everything that we did before. We did the multiplication and so on. But now what we do is we do the brute force. With the brute force, we'll go from 1 to 1,000,000 in this case, calculating the new values of g to the power of x until we find the value that is our result. Once we find it, we'll print it out. So here we go. Let's do 54 plus 12. And the result is 66, which is correct. So what it's actually done there is it's went through all the values from 1 up to 66, doing g to the power of 66 mod p, and p values here. And then when it finds a value that equals that, it knows that it's found the sum. Okay, so that is how we can add, and we can also do this the same with subtraction for this. Okay, so that's been a quick overview of how we can do homomorphic encryption, divide, multiply, add and subtract with discrete logarithms.